be talking about a strong asymptotic global principle for integral Kleinian sphere packings. To get an idea of what I'm talking about, I'm going to talk about a specific, we'll begin with a specific example of a integral Kleinian sphere packing, and that particular example is a Soddy sphere packing. So with the Soddy sphere packing, we begin with 4 mutually tangent spheres. And then we put in more spheres that are tangent to the initial 4. And then in each space that you see there, we put in another sphere. And we keep on doing this over and over again until we get a Soddy sphere packing. So if you look at this picture, you'll notice a bunch of numbers on the spheres. The label on each sphere is the bend, which is 1 over the radius of that sphere. In this particular example, all the bends are integers. This occurs frequently enough that number theorists are interested in this. And a natural question to ask, given that all these bends are integers, is which integers appear as bends? To answer this question, number theorists would start by answering the question, are there any congruence or local obstructions to the numbers that can appear? So towards that, we have our definition of admissibility. For let P be an integral Soddy sphere packing, an integer m is admissible or locally represented if for every positive integer q, m is congruent to the bend of some sphere in the packing mod q. Equivalently, m is admissible if and only if it doesn't have any local obstructions. So in order for an integer to be a bend, it has to be admissible. Just because it has to have satisfy, there should not be any congruence or obstructions for it to be a bend. So, what Koncharovich proved is an integer m is admissible in a primitive integral Soddy sphere packing P if and only if m is congruent to 0 or epsilon of p mod 3, or epsilon of p is either plus or minus 1. And it depends only on the packing. So here primitive means that the greatest common divisor of all the bends in the packing is 1. So in our particular example, m is admissible if and only if m is congruent to 0 or 1 mod 3. Any questions so far? What? Okay, sorry. Congruence, there's some issue with the congruence, like it cannot be. So in this particular example, if m is congruent to 2 mod 3, it cannot appear as a bend. Does that make sense? And that is a local obstruction. Okay. So is there a marker somewhere? So okay. So if I have an integer that is 2 mod 3, it cannot appear as a bend in this. That is the local. Does that
It's local at prime 3. So 3 gives you condition. And you can look at mod 3. They give instructions. So if you see something that's too much, it's forbidden. So you can choose another prime. Say, all right, you can choose another number. 7, 9, 12, or something else. And I say for instruction mod 12. Does that make sense?
Yeah, that's a great explanation. Should we wait for Fang-Ting to get back or? Okay. So admissibility doesn't tell us everything. For example, the integer m equals 0 would correspond to so a sphere with bend 0 corresponds to a plane, but we don't have any planes running or you'd say flying around here. So we need something more than just admissibility. And this something more is sufficiently large. So Kontorovich proved the strong asymptotic local to global theorem that says that the bends of a fixed primitive integral Soddy sphere packing satisfy a strong asymptotic local to global principle. This means that there exists an n naught such that if m is greater than n naught and m is admissible, then m is the bend of a sphere. And in this particular example here, if m is congruent to 0, 1, mod 3, and m is sufficiently large, then m is a bend of a sphere in this packing. It is believed that n naught equal to 330 is actually sufficient for this particular example, but no one has actually proven it yet, because in order to prove that, you would have to figure out you would have to explicitly compute all the constants, and no one has actually done that, even though all the constants involved in this theorem are effective.
Just one question. To be admissible, principle, you have to check all primes for all numbers Q.
Right.
So here you only have the prime 3 to give the number to play.
Right.
For this example, there are no other instructions at any other place.
Correct.
Okay, that's a non-trivial statement.
Yes.
Okay, so
That
3
is
is the only possible instruction. Okay.
For this particular
For this
fact.
example. And I guess is it a fact that for any packet finite number of
If it's created in a certain way.
okay.
So if it's a Kleinian sphere packing, yes.
So there are a finite number of potential obstructions. And then when you're beyond a certain bound, once those obstructions are filled, it passes all those tests, then there is this.
So Soddy sphere packings, yes. For other sphere packings, yes and no.
Okay, go on. Just trying to clarify. Thank you.
Yeah. / it might not be proven yet for other packings, which is what I'm going to be talking about. Okay, so here's a brief outline of how Kontorovich proved this result. He showed that the automorphism group / the symmetry group of the Soddy sphere packing contains a congruent subgroup of PSL2 of the Eisenstein integers. And this congruent subgroup maps a particular sphere to itself. So when I say automorphism group or symmetry group here, I mean like a group generated by reflections or Mobius transformations. So consisting of reflections or Mobius transformations. And I'm talking about reflections through circles, but anyway. anyway, so with this condition, we know that the set of bends contains the primitive values of a shifted quaternary quadratic form. And by a shifted quaternary quadratic form, I mean a quadratic form in 4 variables, but there's some constant added. And primitive here is in quotation marks because the primitivity condition is actually a coprimality condition in the Eisenstein integers. Okay. So the shifted quaternary quadratic form gives you enough to work with. So you can quote the result of the circle method to say that every sufficiently large admissible number is represented by the quadratic form, the shifted quadratic form, without the primitivity condition. And what Kontorovich actually spends a lot of time doing is showing that a singular series that contains all the local information, so all the congruence obstructions, all the congruence restrictions, that's contained in the singular series. He spent a lot of time showing the singular series with the permittivity restriction is bounded away from 0 when M is admissible. The issue is if the singular series gets too small, then in the circle method you have some error term, and if the singular series is too small, the main term is actually smaller than the error term, so you start having some issues trying to say that a number is represented. Okay. So I'm going to define what I mean by a congruence subgroup of PSL2 of the Eisenstein integers, actually for a ring of integers. For an imaginary quadratic field K, a principal congruence subgroup of PSL2 OK is a subgroup of the form here, where so the matrices that are congruent to the identity mod some fixed element in our ring of integers. And the Scisphere packing case, there exists a sphere in the packing such that the stabilizer of the sphere and the automorphism group contains up to conjugacy the congruence subgroup here where B and C are congruent to 0 mod rho, where we're taking matrices in with entries in the integers, and rho is 1 plus e to the pi I over 3. Any questions before I start talking about general Kleinian sphere packings? So, as I said, a Scisphere packing is a specific example of a Kleinian sphere packing. There are actually infinitely many Kleinian sphere packings and infinitely many integral Kleinian sphere packings. So we have our Scisphere packing on the left. In the middle is an orthoplicial sphere packing that and on the right is the fundamental domain of another sphere packing. So given these few examples, I should probably tell you what the definition of a Kleinian sphere packing is. So an n-1 sphere packing P is Kleinian if its limit set is that of a geometrically finite group gamma of isometries of n+1 n+1 dimensional hyperbolic space. So That's saying a lot. So in this particular picture, our group gamma is generated by reflections through these hemispheres. And if you look here in the right there, it kind of looks like you have a circle packing there, right? So what I'm saying here is if I took a point in hyperbolic space, looked at the orbit of this point by this group generated by reflections through those hemispheres, the limit set of that is a circle packing, in this case, the Apollonian circle packing. And yeah, an Apollonian circle packing is a two-dimensional Kleinian sphere packing. How you can also have, it's the limit set of, the Apollonian circle packing is the limit set of a group of isometries on hyperbolic, three-dimensional hyperbolic space. The sphere packings that I showed on the previous slide are they're the limit set of groups of dimensionally finite groups of isometries of four-dimensional hyperbolic space, but it's kind of hard to show that. Kind of hard to draw four-dimensional hyperbolic space, so I kind of had to go with the Apollonian circle packing.
Excuse me, when you say geometric, you mean it's a finite group?
Nope.
So what do you mean by? So I see three. It's
yeah, it's a technical definition.
Yes.
It means that the convex, an epsilon thickening of the convex core of the fundamental domain has finite volume.
Okay. Yeah.
Yeah.
Okay. I think I'm getting. So these are finite generated.
They're not finitely.
They're not finite generated.
Yeah.
You're telling me that.
These, it can be, but they are not necessarily.
Oh, okay. So in this case, it's generated by three spheres.
Technically four, but yes.
Four, or let's say four spheres.
Yeah.
Those are reflections generated.
Mm-hmm. So in this case, it is finitely generated, but in general, yeah, it's actually a weaker. It's a weaker condition. If you're finitely generated, then you won't be finite.
Okay.
So, yeah. So some important things to know about Kleinian sphere packings is the action of isometries of n+1 dimensional hyperbolic space extends continuously to Rn hat, which is Rn union the point at infinity. And this is the boundary of n+1 dimensional hyperbolic space. Another thing is the group gamma that is in our definitions stabilizes our packing or acts on our packing. It maps the packing to itself. And this group gamma is what I'm referring to as the automorphism or the symmetry group. And one little tidbit here. Our group gamma is a thin group, which means that it has infinite index in its heuristic closure. So, what am I doing? My goal is to prove strong asymptotic global principles for certain integral Kleinian sphere packets. That is, prove that if M is admissible and sufficiently large, then M is the bend of n minus one sphere in my packing, where my definition of admissibility is very similar to what we had in the Scisphere packing case. So an integer M is admissible or locally represented if for every positive integer q, M is congruent to the bend of some n minus one sphere in our packing. So more technically, what am I actually trying to prove? So this is a main theorem that's going into my dissertation, and I'm still working on it. Let P be a primitive integral Kleinian n minus one sphere packing in Rn hat with an orientation preserving automorphism group gamma of Mobius transformations. Suppose that there exists an n minus one sphere S naught, such that the stabilizer of S naught in gamma contains up to congruency a congruent subgroup of PSL2 OK, where K is an imaginary product field, and OK is the ring of integers of K, the set of this condition implies that n is at least 3. So I'm working with at least sphere packings or hypersphere packings. I'm also assuming that there is an n minus one sphere S1 in our packing that is tangent to S naught. And this last condition is, I'm assuming that a ring of integers is a PID, a principal ID domain. With all of this, I'm trying to prove that every sufficiently large admissible integer is the bend of an n minus one sphere in the orbit of S1 under gamma, which is a subset of our pack.
Just remind me a little bit. For OK to be a principal, I built up. Is that fine?
Yep.
Okay, I'm just trying.
Yep.
So it's that finite list of 10 or whatever.
Yeah.
Okay.
Yeah. Oh, yeah. So there's reasons for all of these conditions. The first one is probably the most important condition here. The other two, they're there for more technical reasons. So. It's difficult to prove right now. I'll talk about those two conditions, how they enter into my proof. The expectation it would be the expectation is you should be able to have this theorem without conditions, the last two conditions. Just with that one. Yeah, just that first. That's the expectation. Yeah. So that's the expectation. That being said, yeah, there's reasons for the second and third conditions that I will talk about later. Okay. So before we get too far, why should we have a strong asymptotic global? So it has been proven that if we have a Kleinian n minus one sphere packing with n at least 2, the number of spheres in our packing with bend at most n, counted with multiplicity, is asymptotically equal to a constant times n to the delta, where delta is the Hausdorff dimension of the closure of our packing. So for us, delta is greater than n minus 1, which is at least 2. Thus, we would expect the multiplicity of a given admissible bend up to n is roughly n to the delta minus 1, which is bigger than n. So we should expect every sufficiently large admissible number to be represented, actually be represented quite a few times, like n times. So given this, like, I'm trying to prove this aspect of the global principle. I'm going to go through the proof outline here. The assumptions that the stabilizer of S0 in Vienna contains the congruence of the proof of PSL to OK, and that S1 in our packing, S1 is a sphere in our packing, is tangent to S0, imply that the set of bends contains primitive values of a quadratic polynomial in 4 variables. And here primitive is in quotation marks again because it's a coprimality condition for integers in our for elements in our ring of integers. This quadratic polynomial in 4 variables should give you enough to work with, so you can apply the circle method to show that every sufficiently large admissible integer is represented as a bend. I'm going to go into more details how I go in, how I'm into this. I'm going to go into more details of this proof. But are there any questions so far about the statement?
Can you show us maybe one example?
It's not easy.
So how is this polynomial?
That's what the next several slides are about. I'm not kidding. That's seriously what the next several slides are about. Okay. So let's start with isometries in hyperbolic space. So I'm letting a bit of notation. I'm letting isom 0 h n plus 1 to be the group of orientation preserving isometries of n plus 1 dimensional hyperbolic space. I'm letting mauve 0 Rn hat be the group of orientation Mobius transformations acting on Rn hat. It's known that these two groups are isomorphic.
Excuse me, just to clarify, Rn hat is not a sphere. What is it? You compactified Rn.
It's a 1 point
It's the 1 point. So that is, in a sense.
Mhm.
Okay. All right. Just trying to get a picture.
Yeah, it's just our Rn union
With a 1 point.
with infinity attached. Yeah.
Okay, so that's the sphere. Yeah.
Yeah, pretty much.
Okay.
Yep. Actually, yes, it is a sphere.
Yeah. Okay.
Yes.
I don't know how you picture it, but I mean,
Yeah.
that is.
No, this is actually an important point because, like, I often normalize so that one of the spheres I feel
Is that infinity or something? But
It
anyway,
has a point.
I just want to make clear in my mind. Is a sphere. Okay.
yeah. So, yeah. So the important thing here is how they act. They act via Mobius transformations. If you take a complex analysis class, this looks like something like AZ plus B times the inverse of CZ plus D. In this case, A, B, C, and D are all in a Clifford algebra with some restrictions, and A, B, C, D are entries in PSL2 of this Clifford algebra.
If I take n equals 3, is that Clifford algebra?
Okay, so actually, yes, that will help.
Well,
It will help, and I'm actually going to talk about this on the
okay.
very soon. Okay, like the next slide. Okay, so a Clifford algebra ZM is a real associative algebra generated by M elements, I1, I2 through IM, subject to the relations that if you square any I, you get -1. And if I switch the order of any two i's, I get a negative sign. So C0 is actually the set of real numbers. C1 is isomorphic to the set of complex numbers. Under the isomorphism, you send I1 to I. C2 is isomorphic to the set of quaternions. Under the isomorphism, you send I1 to I and I2 to J. C3 is isomorphic to a direct sum of the quaternions. I will not talk about the exact isomorphism because it's actually a lot harder to say than the previous one. So Clifford algebras extend our notion of the complex numbers and the quaternions. So embedded in our Clifford algebra, we have Clifford vectors, which are the set of elements in which each term has at most one I appearing in it. So things of this form. And this set of Clifford vectors is isomorphic to Rn, and we can do the 1-point simplification here. And by adding infinity to our set to get an identification with Rn hat. So this is useful because now we can have our Clifford algebra act on elements in Rn hat. So when we're talking about Mobius transformations, I'm going to go back to an example that you learned in complex analysis. We have the group of Mobius transformations on R2 hat is isomorphic to PSL2C, which acts on our 1-point compactification of the complex set of complex numbers by the mapping AZ plus B times the inverse of CZ plus B, where A, B, C, and D are all in the complex numbers, and the matrix with those entries is in PSL2C. Restrictions make explicitly stating what our set of Mobius transformations is isomorphic trickier for higher dimensions. For example, the set of Mobius transformations on R3 hat is actually not isomorphic to PSL2H, even though the Clifford algebra C2 is isomorphic to H. There's just a bunch of more conditions that I'm not going to go into during this talk. What do you mean? What? So this is contained in. So the set of Mobius transformations is contained for R3 hat is contained in PSL2 of the quadratic. Any other questions? So in order to get our Mobius transformations acting on spheres, we need to be able to talk about how we're parameterizing spheres. And to do this, we use inversive coordinates. So given a oriented generalized n-1 sphere S, we define the inversive coordinates of S to be the ordered triple beta, beta hat, and Cassie, where beta of S is the bend of S, which is 1 over the radius of S. It's taken to be positive if S is positively oriented and negative otherwise. If S is a hyperplane, then its bend is 0. The cobend beta hat of S is the bend of the reflection of S in the unit n-1 spheres centered at the origin. The Cassie is the bend center. So if S is an oriented n-1 sphere, then Cassie of S is just the bend times its center. If S is a hyperplane, then its bend center is a unique unit normal vector of S. The unique normal vector to S pointing in the direction of the interior of S. And with our inversive coordinates, we create the inversive coordinate matrix of S, which is a 2x2 matrix with the entries of the cobend, bend center, the bar of the bend center. So in the Clifford algebra, there is some sort of operation that kind of acts like the complex conjugate, actually is complex conjugate for complex numbers. And then this last entry is the bend of S. So an example, if we have this circle here, it has a radius of 2, so its bend is a half. If we reflect this circle in a unit circle, we end up seeing that the point on the rightmost point of this little circle here, which is the reflection of S through the unit circle, this point here is a half, and the leftmost point is a sixth. Therefore, its diameter is a third, which means that the bend of the little circle here. Oh, the radius of the radius of the little circle is a sixth, which means the bend of the little circle is 6. This means that the cobend of S is 6. And to C of S, our bend center of S is the bend, which is a half, times its center, which is 4, which is identified with 4. It's actually 4, 0, which simplifies to 2, 0. But if we're doing that identification with the Clifford vectors, this is just 2. This means that our inversive coordinate matrix is this matrix here, 6, 2, 2, a half. If our bend center was complex, like let's say 2i, then this entry down here would be negative 2i. Any questions? So
What is the one information?
yeah, so for spheres, you just need to know the bend and the bend center. For hyperplanes, you need the bend center and the cobend, because the cobend actually tells you how far your hyperplane is from the board. And then your bend center would tell you which way your plane is pointing. Yeah. So we're going to put, so I talked about Mobius transformations, and I've talked about inversive coordinates. Let's put them together. So the group, yes, SL2 of our Clifford algebra C n minus 1 acts on the set of inversive coordinate matrices by this action here, where M is an inversive coordinate matrix and G is in our is in SL2 of C n minus 1. So here SL2 C n minus 1 is denoting is like representing a Mobius transformation. And this group action on the set of inversive coordinate matrices is equivalent to the group action of SL2 CN minus 1 on the set of oriented generalized n minus 1 spheres. That is, if S is an oriented generalized n minus 1 sphere and D is a matrix in SL2 C n minus 1, then we have the inversive coordinate matrix of G of S is the same as G acting on the inversive coordinate matrix of S. This extends work that has been done by Kate Sting for n equals 2, Senya for n equals 3, and Matt Littman and Senya for n equals 4. They did not do this for quite yet. So a corollary of this lemma is that if I have a matrix G and that represents my Mobius transformation, and S is an oriented generalized n minus 1 sphere with the inversive coordinates beta, beta hat, and Cassie, G of S naught has these inversive coordinates, which if you look at this, for the bend, it kind of looks like that we have a quadratic in C and D. It kind of looks like we have a quadratic form in C and D. This is, we're using this to get the quadratic polynomial. Let's actually talk about this a little bit more. So I had that, I said that the assumptions that the stabilizer of S naught and gamma contains a two-conjugacy, a congruence subgroup of PSL2 of OK, and that S1 in our packing is tangent to S naught, imply that the set of bends of P contain the primitive values of a quadratic polynomial in Ford carry. For simplicity, we're going to assume that S naught is a hyperplane with inversive coordinates 0, 0, negative I n minus 1, and which we can just do by taking our packing in, mapping one of the spheres to that. And we're going to also assume that S1 is a hyperplane with the inversive coordinates 0, beta 1 hat, I n minus 1, where beta 1 hat is positive. Okay. I'm going to let my ring of integers be generated by omega. I'll let rho be some element in my ring of integers. I'm going to let gamma be some element in my automorphism group, big gamma. And I'm going to let D be some element in the principal congruence subgroup defined by rho, which is, and this principal congruence subgroup is a subgroup of PSL2 OK intersected with my automorphism group, big gamma.
I suppose omega is the cube root of 1.
In the Soddy sphere packing case. In general,
In
is
general, it's whatever it is.
whatever it is.
Okay. Okay.
Yes. Yes. Okay. So if I actually look at the bend of S1 after it's acted on by G and gamma, I get this, which is actually a quadratic polynomial in A0, A1, C0, and C1. You can kind of see that it's a quadratic polynomial in A0, A1, C0, and C1 because of this norm thing. So, and by definition, gamma GS1 is in my packet. So the whole question of if a certain bend occurs, I've turned it into, can I write my, can I write a number in this form? Note that here only A0, A1, C0, and C1 appear. So it's only these two entries of this matrix B. B0, B1, D0, D1 do not appear. That's because I assumed that S1 is tangent to S0. If I did not assume that, all my A's, B's, C's, and D's would appear here. So, okay. I have this quadratic polynomial. I'm actually going to give it a name, f sub gamma. And I'm looking for things represented by this quadratic polynomial such that a0, a1, c0, c1 are integers, and this this element and this element are relatively prime in my ring of integers. And the reason why is, if we go back here, they're in PSL2 OK. It suffices that these two elements are co-prime in order for me to have an element in a matrix, in my matrix group. It suffices for these two elements to be co-prime to find a matrix that G. So this condition I'm going to call the coprimality condition. And what I'm actually, so now what I'm interested in is which integers are represented by my quadratic polynomial as gamma, a0, a1, c0, and c1 vary subject to my coprimality condition. So to do this, I start counting how many times an integer is represented in this form. So that's what this number Rn of m is doing. So big N is t squared times x squared, where t is very small compared to x. Upsilon sub x is a non-negative bump function that pretty much says that a0, a1, c0, c1 are all about the size of x when I'm doing this count. And this thing here is my indicator function that pretty much it's 1 when m is equal to my quadratic polynomial and 0 otherwise. So I'm essentially counting the number of times m is represented by my quadratic polynomial, subject to a bunch of other conditions, mostly that a0, a1, c0, and c1 are all of size x. And we want to know when Rn of m, our representation number, is positive, because if it's positive, then m is represented as a bend. Okay. So let's go through every single part of this representation number, like why is it there and how it's being handled. So this first sum over the gamma, where gamma, the entries of gamma are at most of size at most t. This addresses the admissibility conditions. That is, it makes sure that my singular series is not too small, which was an issue with the Soddy sphere packing proof, if you recall. In order to do this, I'm using a little bit of spectral theory and extender graphs. So here we have the coprimality condition. It can be removed by using the Mobius function on ideals. However, currently, in order to remove this condition, we need to use the fact that our ring of integers is a principal ideal domain, since our quadratic polynomial is not invariant over ideal. And this part summation over A naught, A1, C naught, C1, and Z is handled using the circle method with a Kloosterman requirement. And this obtains the bulk of our main term and our error term. So some future directions. Remove the condition that our ring of integers is a principal ideal domain. Again, this is more of a technical detail and shouldn't be actually a real difficulty. It's just a lot more challenging to do the calculations if it's not a PID. Another future direction is remove the condition about S1 in our packing is tangent to S naught. So you would end up with a quadratic polynomial with 8 variables instead of 4, but that coprimality condition, it actually becomes a lot more difficult because you actually needed the determinant equal to 1, and it's a lot harder to actually figure out what that's true. And another future direction is actually figuring out how large is sufficiently large, because, well, all the constants involved in this theorem are effective, so you could actually compute them, but no one has actually computed them, / the theorem is still in progress. So I should say where my illustrations came from. So besides the illustrations that had the citations in next to the picture, and a few of the illustrations with circles in them, pretty much all the illustrations came from this paper by Alex Koncharovich. And thank you for listening.
Have you ever heard of Lie sphere geometry? So much of your talk might the whole thing. You know, so Lie, before he became Mr. Lie groups, he studied the space of spheres in Euclidean space. And he introduced what we call Lie quadratic methods. It turns out it's a symmetric space. And in fact, theory of Clifford algebra, modern treatment, in the study of sphere geometry.
You said Lie sphere geometry.
Lie sphere geometry. I'll send you a book on it.
Okay.
It strikes me with non-trivial intersection. That is about, but it's very specialized. It's the case. So I'm not an expert on sphere geometry, except I know it exists. And I know it has to do with Clifford algebra. It's one of the ways we study it. I don't think that Sophus Lie introduced Clifford algebra is part of the Lie groups. Of course, there are Lie groups here. They're very special. They're ESL, like the Quaternions and so on. Those are. So I'm curious about the connection. Common.
So in those pictures, like theory would be
So yeah. So in theory, yes, the issue is with the circle method. So the circle method, it works better with more variables. For quadratic forms, you actually need to have at least 4 variables. Yes.
Is it the case like the sphere packing is a unit circle, then you put 2 circles inside, and then you're adding more and more?
That's an Apollonian circle packing, and that's integral.
So what For that case, is that everything's known for the obstruction.
Yes, they happen. They occur modulo 24.
Okay. Before is the
Mhm.
And for the bound is that beyond number.
What do you mean by which thing?
In your statement here, you have lines of obstruction, the other one is systems. Everything beyond that. As long as it's admissible.
Everything should be effective, and